We will now take a cursory glance at Chapter 10 regarding power series. Now, power series are not to be confused with p-series. Remember, in Chapter 9, we took a look at a p-series, something like this: the sum from k equals 1 to infinity of 1 over k to the p. If we expand it, it would look like something such as 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus ... continuing indefinitely. We learned that if p is greater than 1, the series converges, and if p is less than 1, the series diverges. So p was a real number. So this series is simply a sum of real numbers. A power series, on the other hand, is going to look more like a polynomial containing a variable. In section 10.1.1, we'll begin our approach to power series by looking at polynomial approximations of elementary functions. Here's a definition to begin with. A power series is an infinite series of the form, the sum from k equals 0 to infinity of c sub k times x to the k. So we're still dealing with series, infinite series to be specific, and we could expand this by incrementing k by 1 from 0 to infinity. When we expand it, we get c naught plus c sub 1 times x to the first power plus c sub 2 x squared plus, and we would continue this pattern to the nth term, c sub n x to the nth power plus ... we would continue that indefinitely. Now let's pause right there just for a minute and go back and visit our friend, the geometric series. We could define the geometric series as the sum from k equals 0 to infinity of a r to the k. A is a constant, r is also a constant. So if we expand this, it looks like a plus ar squared, and we would continue this till we get to the nth term, ar to the nth power, and then we can continue that indefinitely. That is the geometric series. It looks a lot like the series that we're attempting to define here. There are a couple of differences between this geometric series and this new power series. First of all, notice that in the power series, the coefficients change term to term. C naught, C1, C2, the subscripts there indicate that you're dealing with distinct real numbers, whereas the a in the geometric series is a constant. That's going to filter through to all of those terms. Also, in the power series, x is increasing in power. X represents a continuous variable, whereas in our geometric series, r is increasing in power. R is a constant. So like the p series, the geometric series is the sum of an infinite number of constants. And of course, the difference between the geometric series and the power series is that the power series contains this variable x. So even though the geometric series and this power series do have a resemblance of each other, the power series looks more like a polynomial of infinite degree. Now, we could generalize this. We could also express the power series as the sum from k equals 0 to infinity of c sub k times the quantity x minus a to the k. So what I'm changing here is the way the variable looks. The original power series had an x. This one now has an x minus a. So if we think about transformations from college algebra, this second one, if we were to think about the graph of this infinite degree polynomial, whatever that would look like, this one would be that polynomial shifted to the right by a units, if a is positive there. When we expand this more general form, we still have what resembles a polynomial of infinite degree. Now, this number a we call the center of the series. And now I'm sorry here, I filled in the blank for you. This is supposed to be coefficients. Surprise! The coefficients, c sub k, are real numbers. The set of values of x for which the series converges is called the interval of convergence. Now let's pause right there for just a minute. We can go back to our geometric series and remember that this series converged for r less than 1. So if this ratio is less than 1, then the series converges. Now, we've got in this series a variable, so we would need to figure out over what values of the domain of this function would that series converge. So instead of having one specific r value like we do with a geometric series, we're going to have a range of possible values for where this series could converge. Now, related to the interval of convergence, there is something called a radius of convergence. The radius of convergence, r, is simply the distance from the center of the interval of convergence to the boundary. So to keep it simple at this point, a power series can be thought of as a polynomial of infinite degree. Now, before we get to the polynomials of infinite degree, we're going to start with polynomials of finite degree. And let's consider this problem. Find a polynomial function, p of x, whose graph resembles the graph of an elementary function, f of x. Now, that elementary function will be some sort of familiar function, such as square root of x, e to the x, sine of x, 1 over x, etc. It can be algebraic or transcendental. Example 1 illustrates this. The polynomial function p of x equals 1 plus x squared, that's supposed to be over 2, resembles the graph of f of x equals e to the x on a small interval about x equals 0. So f of x is what we're calling our elementary function, and we're approximating it with a polynomial function. Specifically, this polynomial function is of degree 2. So if you look at the graph, the blue curve is p of x, the polynomial function, and the red curve is f of x, our elementary function or our exponential function. The statement there says p of x approximates f of x on a small interval about x equals 0. So if I look at x equals 0, this would be the point 0, 1 on the graph. If I don't move very far away from 0, if I consider a very small closed interval around x equals 0, then the red curve and the blue curve are practically indistinguishable. So on a very small interval, I could replace e to the x with this polynomial function because they're so close. However, as we move away from x equals 0, let's consider a larger interval, -3 to 3, then the curves are very distinct. The further that we move from 0, the greater the distance between the two functions, and they begin to separate from each other. So I would not want to replace e to the x with this polynomial function on the entire domain from -infinity to infinity. I could only use that polynomial as a replacement on a very small interval around x equals 0. So in example 1, the polynomial function was given to us for comparison to the elementary function e to the x. But suppose that we wanted to find a polynomial function to replace e to the x. Well, our replacement polynomial function would have to satisfy some conditions. First of all, number 1, the polynomial function p evaluated at some specific input value, which we're calling c, would have to match the elementary function's value at c as well. This simply means that both functions pass through a common point. In the case of example 1, both functions contained the point 0, 1. Also, condition number 2, p prime of c would have to equal f prime of c. That is, both functions have the same slope at x equals c. So if we go back up to our example, if we take a quick derivative, f prime of x, of course, is e to the x, and the derivative of e to the x at 0 is 1. For our polynomial function, the first derivative is 1 plus 1/2 times 2x, or x, and the slope at 0 is the same. So our elementary function and our polynomial function had the same slope. Number 3 condition, the second derivative of the polynomial should match the second derivative of the elementary function. That is, both functions have the same concavity at x equals c. Now, we could continue imposing further conditions, finding higher order derivatives, and as we do that, that's going to give us a better approximation, a polynomial approximation of the elementary function. Now, believe it or not, you have done this before many times, specifically in Calculus 1. when you find the equation of a tangent line, ultimately you're finding what's called a linear approximation. You may not have called it that at first, but technically that's what you're doing. Note, a linear approximation for a curve at a point is basically the tangent line at that point. The tangent line shares the same slope as a curve at a specific point. So we could say the tangent line is a degree 1 polynomial function that approximates an elementary curve. We know that the tangent line looks a lot like the curve on a very small interval, but on a larger interval, we can distinctly see the difference between the tangent line and the polynomial function. Now, because you are proficient at finding the equation of a line tangent to the curve, instead of looking at a degree 1 approximating polynomial, let's go for a second degree in example 2 here. Find a second degree polynomial function that approximates f of x equals natural log of x at x equals 1. So we want to find a quadratic function or a parabola that's really close to our natural log function around x equals 1. So we're going to look for a second degree polynomial function. I'm going to call it p sub 2 of x. The subscript here indicates that I'm looking for a degree 2 polynomial function. And I'm going to write this as a naught plus a sub 1x plus a sub 2x squared. So the coefficients, the a's there, represent real numbers. So I've simply designed a general quadratic equation or a general degree 2 polynomial equation. Now, I'm just wondering, is the way that I have written it, does it bother you a little bit? Did you think, why is she writing that in ascending order? Normally we write polynomials in descending order. Well, that's true unless you're dealing with power series. Ultimately, we're going to go from finite degree polynomials to polynomials of infinite degree. So we can't really write those in descending order because we don't have anywhere to start, because infinity is the idea of increasing without bounds. So what we do with an infinite degree polynomial is write it in ascending order. We start with a constant and allow the powers of x to ascend up to infinity. So our goal here is to find the coefficients a naught, a sub 1, and a sub 2, real number coefficients that would create a quadratic function or a parabola that looks like natural log of x. So we want to make sure that p sub 2 of x and f of x meet those conditions. That is, we want the function values to be the same, the first and second derivatives to be the same. So let's find the first derivative of our polynomial function. We could write it a sub 1 plus 2a sub 2x. And our second derivative, by the way, I'm going for a second derivative because I'm finding a second degree polynomial. So the derivative here would be 2 times a sub 2. Let's go ahead and evaluate the polynomial and its derivatives at our target value, that is x equals 1. So if I plug in x equals 1, p sub 2 of 1 becomes a naught plus a1 times 1 plus a sub 2 times 1. P sub 2 prime of 1, again, I'm just plugging 1 in for x, is going to look like a sub 1 plus 2a sub 2. And finally, p sub 2 double prime of 1 looks like 2a sub 2. Okay, let's hold that thought for a minute because we want to go ahead and establish a relationship between our approximating polynomial, which we're calling p sub 2 of x, and our elementary function, which we're calling f of x. So our function f of x is natural log of x. We're going to go ahead and find the first two derivatives. F prime of x, of course, is 1 over x, and f double prime of x then would be negative 1 over x squared. Now remember, we want our approximating polynomial function to match the given elementary function f of x in y value, in first derivative, and second derivative. So we're going to go ahead and evaluate our elementary function and its derivatives at 1 as well. Natural log of 1 is 0. F prime of 1 over 1 gives us 1. And f double prime, when we plug 1 in for x here, we get negative 1. All right, now we have something to work with. We're going to set p of 1 equal to f of 1. This is going to give us the equation. P of 1 is a naught plus a sub 1 plus a sub 2, and we're going to set that equal to f of 1. Similarly, we're going to set p prime of 1 equal to f prime of 1. We're setting up our parabola to match the given elementary function in slope. So I'm taking p prime of 1, setting it equal to what we obtained for f prime of 1. One more condition, we want the second derivatives to match. Imposing this condition gives us the equation 2a sub 2 equals negative 1. Observe we have a system of 3 linear equations in 3 variables. This one's going to be pretty easy to solve using back substitution. Notice out of this last equation, I can go ahead and solve for a sub 2 to get negative 1/2. Then I can take that value back to this equation and plug it in. A 2 times negative 1/2 gives us negative 1. So a sub 1 then would be equal to 2. So I've got 2 coefficients here. I'm going to plug in the 2 that I know up into this top equation. A naught plus the value we got for a sub 1 plus the value we got for a sub 2, all of that should be equal to 0. So a naught then would give us negative 3/2. Okay? Sorry for the crunched up work there. Okay, so we can make our conclusion. We can say, therefore, the polynomial p sub 2 of x, I'm looking at this for my format, which is equal to a naught, we found negative 3/2, plus a sub 1, remember we got 2 for a sub 1 times x, plus a sub 2, that's negative 1/2 times x squared, resembles the function f of x equals natural log of x around x equals 1. Observe I'm using very general language here just as to get kind of an overview. We could be more specific, but we're not going to at this point. So notice our second degree polynomial function is a parabola which opens down, which resembles our natural log function. Now let's take a peek at the graph of these two functions. The red graph is our function natural log of x, and the blue graph, that's the polynomial function that we found. So we have a parabola that opens down. Our point in question here is 1, 0. So notice the two functions share the same point. They have the same y value. If we imagine the tangent line there, we can see they have the same slope. And in addition, they're both concave down, so their second derivatives match as well. So on a very small interval around x equals 1, the polynomial function and the natural log function are indistinguishable. The further away from 1 we move, the more we lose accuracy in replacing that natural log function with the polynomial function. Now, why would I want to do that? What we're going to see is ultimately you can replace any function, transcendental or algebraic, with a polynomial function. Polynomial functions are very easy to work with. They're easy to graph, they're easy to integrate, they're easy to differentiate, they're fairly easy to solve. So if you have a difficult function to either integrate or differentiate, you can replace it with an approximating polynomial and work with that polynomial in its place. So these are very useful in simplifying many types of problems.